Terrific. Thanks very much, and thanks everyone for your attention. It's great to be back here at Sorbonne and at FSIC. We were just saying I was last year in 2019, and it's grown quite a lot. It's great. I'm Dan Fritchman. I'm here from UC Berkeley, and I'm going to talk about software for analog design. First, how I come to that problem is basically through the route of an analog designer. That's how I've spent most of my career, a lot of that at Apple, working on IP for the mobile SoCs. The last few years, including really the entirety of my time at Berkeley, has been on software for that field. And before I get into, there's really two pieces of software I want to show you today. Before we get into that, a little dispatch from Berkeley, and one of the fun things we do there, which is our most fun course, as of a little over 2 years ago, say a group of students, about half undergrads, half grad students. We lock them in a room for the semester, and we tell them we'd like you to produce this pretty elaborate mixed signal chip with an RF transceiver, a processor, AES hardware acceleration, and really get it fabbed, really get it made, really get it back into the lab for the next semester. And that was such a round success that the following 2 years, we decided to go even crazier and turn it up to 11. That was about 18, 20 students at the time. This year, we just finished a version that now includes all of that stuff, plus this fun list of switch cap DC-DC regulator, biosensor ADC, a 96 gigahertz radar transceiver. The RF now gets kind of crammed into one corner of this thing. This is in Intel's fab right now. Oh, and by the way, that's one of 3 chips that these students made in this semester. There are now about 60 of them involved. I show these both to show off the great work that my students did, but to point out that my sort of half of this thing, which is the left half, really looks up to the folks in the room on the digital half as far as open source goes. I mean, I think it's a great mechanism for sharing this content, for getting more people involved, and ultimately for making these things better. And as a case study, you're welcome to get the design materials for this half, at least to the RTL level. This is all written in Chisel. And you can get access to nothing from this half. You can't publish any of it. Now, there are lots of reasons behind that. Some of them are non-technical. Some of them we won't be able to help today, but some really are technical. And some, I think there are a few bridges we're going to have to build. And hopefully the software we're going to see today is going to help build a few of them. So the 2 pieces of software are going to be called Hdl21, and another one that's going to be more of a surprise. To introduce what Hdl21 is for, I have a little thought experiment I call the dinner party test. It's basically how well do you understand something? Can you explain it to people who are smart but don't know your stuff? A couple quick examples. If you're asked to describe, say, to your mom or someone you meet at a dinner party, what is this? My description is kind of, this is like a list of instructions for your computer to run. It kind of goes top to bottom. It does one thing, then the other. There's a few special things that change the sort of control flow. Test 2, this will look familiar for Skywater fans. I would describe this as a blueprint. Right? This is a 2.5 dimensional picture of what to fabricate on a chip. X and Y are the die surface, and the colors are sort of Z-axis labels of how far into and out of the screen you want to be. And the third test, and really the point of this, the one that I think is really hard, even for me, despite having spent most of my career on this, is this picture right here. Now, I know this is a schematic, I know it's an op-amp, but also on some level, I really don't know why we imbue so much value to these little squiggles of lines, and why this is so much more satisfying a description of this circuit than some others we'll see. But if we look at real schematics, if you've been in the field, in fact, I started to say we saw a few this week, that most real schematics you encounter look a little more like this. This is not the best visual in the dark, but it's 2 big rectangles with about 500 wires in between them. I would submit this is not the best, most descriptive, best way to determine whether this thing is right for any circuit. And that was this premise of these schematics are one bottleneck in getting our analog tribe to share their work, to better state what it does, was really the genesis of the first piece of software we're going to talk about, which is called Hdl21. This is an analog hardware description library. This is the closest projects that we've talked about this week include Amaranth, and the one that I know most from close to home is Chisel. And the idea is take the things that the circuit designers are used to, the sort of core concepts, modules, signals, and the like, and expose them in the most straightforward way I can think to, in the most straightforward place I can think to make them a program. The first thing to make this as straightforward as I can, and I'm sort of new to expressing this because it's only recently come to my attention that people don't believe you can just do this. Usually our sort of analog and EDA software is like a month-long setup, but really pip install Hdl21 and import it, and then you're off and running. You're welcome to do that while we talk here. By the way, while I talk, there will generally be a QR code on the screen, which is, if you're interested in whatever the content of the slide is, it will usually link to whatever I'm talking about. So what do you get when you import Hdl21? By convention is H. This sort of core thing, very much like in Verilog and Chisel and many comparable pieces of software, is called a module. That's the central hardware reuse element. The usual way that we define these, and kind of a pattern in Hdl21 code, is if you have this sort of pile of connected stuff, it's a class with a little decorator on it. And inside of the modules, you create things like inputs, outputs, internal signals, and instances of other modules. When I say Hdl21 is analog, one of the things that I mean is really the differentiation between it being structural versus behavioral hardware, all structural in this case. You can make modules a couple of ways. The class syntax is sort of opt-in. If you like to make them procedurally instead, and in many cases, I for one do too, that works just fine. There's a lot of sugar and magic behind the scenes to make all of this stuff as straightforward and as kind of familiar to folks who come from HDL land as we can think to make it. Now, the sort of second key concept, and this is a term that I think we at Berkeley really overloaded to our misfortune. In Hdl21, generator is a first-class capital G thing. It's a function that returns one of those modules. It's not just any function that does so, but it is a Python function running any Python code you like, manipulating one of those modules however you like, adding ports to it, rearranging its internal content, and ultimately spitting out a result at the end. So this is really the source of the programmability of creating all this hardware. The parameters are arranged into types. There's a lot of runtime type-safe stuff built into Hdl21, and particularly the notion that you have to rig generator parameters into one type, declare it as a data class-looking thing, which is Hdl21 program class, and impose some organization on being able to say, this is what I need in order to produce this kind of module, whatever it is. We further, when I say this is analog, focus on the things that analog designers need. So things like drivers of SPICE class simulators, Spectre and GSpice and Zeiss are built in. All of the things that go into your typical SPICE deck, all the analyses, measurements, parsing them, getting back into Python is all built in. PDKs, corners, and the like, all built in as well. PDKs, each technology is a Python package itself. We just did a release of the built-in ones that include the major open source PDKs, Skywater, and just introduced GF180. You pull those in the same as any other Python package and start instantiating stuff from them. Or to make process portable modules, they generally each come with a compile method from a set of generic primitives that Hdl21 provides. So there are sort of generic versions of each of the major device types that you'd find in SPICE, transistors, resistors, and the like. And each PDK comes with a method to sort of convert those into its stuff. There's lots of other goodies that, honestly, analog designers don't think they need. They use all the time. The idea of having a bundle, or what System Verilog would call interface of signals, sort of a structural set of them that travel together, is something you'll see all over digital designs. Analog designers will say they don't use it, and then you say you can disprove this in about 1.5 seconds by saying, okay, do you have differential pairs? Yes, you do. Do you have combinations of them? Yes, you do. And there you go. Other things that we build in for the analog tribe that pair very well with those are things like pairs of instances that go with those differential signals. So that is what I would use for almost all analog circuits. I think it's the best way I know to design the kind of stuff we're talking about. There are, however, still some where there is some magic in this picture. And I realize this while trying to help my students prepare and learn these things, just how much harder it is to convey through code what a circuit like this is doing than through this picture. And that realization drove kind of the thesis of next piece of software is called Hdl21 schematics. That is that schematics are really two things: a circuit, and it's also a picture of that circuit. And usually how we've arranged those is in that order. There's some sort of circuit structure and we find some way to render it on screen. Hdl21 schematics, kind of central premise is invert that order. The schematics are in a general purpose image format. And that's SVG, which is an XML-based format that allows you to have custom-defined structure and custom-defined metadata. So these render on platforms like GitHub, and this is not an export of a schematic, this is not a conversion of anything, this is the actual thing that runs, which you can pull up from that link there. And they directly import as the Python generator, Hdl21 generator functions I showed earlier. There are a couple of ways to edit these. This is essentially a web stack editor application. That runs in a couple of different contexts. One is a dedicated desktop app, one's on the web. And the one that was kind of originally imagined runs as a VS Code extension, so a plug-in to the most popular IDE. So in the picture here, code importing the schematic and it at write, in which import it here in the Python code is pulling in the content of this inverter in this file, start making instance of it and go. These are both part of kind of a bigger picture of pieces of software that I'm going to introduce very briefly, just to really point out that they exist. We call that family VLSIR, which is also the name of the central interchange format at the middle of it. VLSIR is defined via Google's protocol buffers. You can think of this as design database via protobuf. There are a handful of pieces of software defined around that. One of the nice things about doing so in protobuf is we can bring to bear a variety of programming languages with a variety of trade-offs for different applications. The three that get used a lot are Python, as you've seen, Rust, and C++. So we have, in each case, what we call a fancy front end. Hdl21 is the prominent one for circuit design. VLSIR is a central interchange format. And then what the LLM folks would call the back-end tools for interacting with other stuff. Industry standard formats, spice simulators, and the like, that come sort of built in. There are a couple such pieces of interaction for layout. The one that is primarily authored by me and some collaborators is called Layout21. This is a series of Rust libraries for sort of progressive levels of detail versus abstraction of programming layout. The two primary ones are 3 layers of note. Raw programming is very much like in the GDSTK or the API-defined K layout that manipulate a thing at a time. The Tetris layer is a much more structured, gridded, constrained approach. And then the Rust packages include all of our parser writers for all the industry standard formats. The other approach, and this is really in a different camp altogether of analog P&R, there have been a handful of US-born projects to do this over the last few years. Our favorite, and the one we work with, is our friends at Intel and a few other universities developed a line. And it is a very helpful realization to note that having circuit code in a general purpose programming language is a great place to embed all of the other metadata and stuff that goes into what you care about those circuits. So this is a work in progress sort of bridge between getting all this data between Hdl21 and producing analog P&R. And lastly, everyone, us included, is into ML for everything, including circuits. a lot of this infrastructure it's not a necessary condition for it, but certainly a helpful condition to start bringing more of our machine learning focused researchers into the fray here. So we have a group of students developing a project called Circuit Gym, which is really a capacity to separate and capacity to enable more of these ML explorations by folks who aren't into all of this circuit stuff over here with all of the very custom to our field tools and process technologies and the like. Okay, so that was a quick whirlwind tour of those projects. I am now going to introduce a piece of software that is new enough it doesn't actually have a name yet. And that is, it's motivated, it certainly flows from Hdl21 schematics, and what its relationship with it remains to be seen. But it is motivated by two realizations. The first, in making that schematic editor, was that would really be of benefit is in building this bridge from our existing analog designs and designers, is being able to work on the schematics they already have. Those are essentially all in Cadence's Virtuoso. That has a data format that is closed source, proprietary, and is licensable for at cost. Second is there's another really helpful enabler that we've already seen, and I see a lot of folks here use, which is the most popular IDE, VS Code, has two very helpful capacities. One I've already shown is the ability to show these WebView sort of iframe style web apps. And two, the one that really has made it just incredibly helpful for our IC world is this remote SSH mode, in which it spins up its own little, think of it as file server on a remote machine, and just serves the content of files over there without actually transferring them, so you can edit remotely directly in this very nice native to whatever computer in front of you UI. So the combination of those, that's a very helpful fact for manipulating the most popular schematic format. And so what's coming soon is an editor in VS Code for the most popular schematic format. This is quite dark and not the easiest to see on the screen here, but this is an open source Cadence schematic. It's from another Berkeley project, BAG. And this gets drawn in Virtuoso. You can publish these open source. It's just you just have to have Cadence to actually show them, render them as a picture. If you want to render it in VS Code as of now, it looks like that, just to say very similar. A very helpful fact about having a modern web stack on my Mac computer, especially for a screen like this, is when I change the display to light mode, you can actually read it. So this is coming soon. I'll flash a few more examples of these, all from the BAG 3 sort of built-in libraries. And how this works is very much the picture I showed, where there is a small VS Code server, and there are essentially two pieces of code. There's the sort of editor UI elements running locally on my MacBook right here, and there's a part that runs on the server, which uses the open access, the schematic formats C++ API. So the plan there is, in short order, that is going to support schematics. This is something you do have to pay for to get access to the format, so this is going to be a commercial product. So this is outside of research. And I think there's a real opportunity to expand that to very much of the analog design environment. So designers are used to sort of a pairing between schematics, simulations, and layout to various degrees of connection. Layout, I think, is different, and we can probably talk separately about how I imagine that'll work. But schematics are coming soon, and simulations coming shortly to follow. So I think I'll demonstrate that. Bear with the technical difficulties, but So here we've got, like I said, the most popular IDE pointed at a machine that's actually not on this continent. Sorry about that. So here we've got VS Code, the most popular IDE. I sit in the back, so I see that many of you have it on your screens throughout most of the conference. And this is a special version, though, because it has the extension in which if I click on a file that is of sort of schematic format, like a few of those that I showed in the presentation, we open a sort of native editor renderer and do not the fully featured set of stuff that you can and eventually will want to do, but go directly into edit of these. If we spin over to split these out side by side, I can't read that, so I'm not going to do it actually. But any of these files that is schematic sch.away shows up like so. So thanks for your attention, and I'd be happy to take your questions.
Hi, thank you for your talk. I just discovered this SSH remote server stuff with VS Code, which looks really interesting for many applications in our domain. And I had a question about the choose of Python for this for your work. And could you comment, because I've seen also that Layout21 was based on Rust. Could you comment on the choice of Rust versus Scala versus Python for this kind of description in terms of expressivity and all that kind of ability in the language?
Yeah, that's a great question. And so first off, the SSH remote mode, if that is news, it is very good news. Because usually a joke that was removed is that the stuff you actually want in our field is always in some server in like the broom closet at the office or at the university, break room or whatever. And this is a very, very nice means of accessing it. On the question of the language support, there are different trade-offs there. And actually, Python and Hdl21 is a very, very conscious pairing. I said the explicit goal is get people who don't see themselves as programmers. In fact, they have a very, very strong attachment in many cases to pictures like this being the content of their work. Give them the most approachable thing that we can think of. And that happens to also be the thing that if they do want to program any other sort of related discipline, if they want to do data analysis, if they wanted to get into machine learning, that it is the most popular and really overwhelmingly most popular language for all of the other things they might want to do. Now that trade-off doesn't apply to everything, right? So there's a very different set of trade-offs for manipulating polygon by polygon layout. I think there's a time-honored tradition of projects trying to use a scripting language or Python to do layout processing and then very quickly realizing, oh my God, this is so brutally slow. So Rust is basically what all of the kind of needs to be performant. I shouldn't say all, we do have a bunch of C++ as well, but is my preference for all of the needs to be performant stuff that's pretty well correlated with stuff that directly manipulates layout. And Scala, there's also, by the way, a long write-up of essentially this question in the Hdl21 README front page. And Scala is, it's bespoke, it's kind of niche, and it's really, we have this great momentum with Chisel, and we've had great success there. But it's very difficult to convince someone who you're really trying to convince to program in the first place that this is the place to start.
Other questions? So this kind of, in my mind, is kind of fitting interestingly with Steph's PDK master approach they talked about yesterday. So have you given any thoughts? Because obviously, like the PDK side, right, and the cell library side, kind of you're dependent on that's kind of like you're basically going to have to be parsing the open stuff there. So PDK master, does give you, can you combine those things together, and how would that work on the layout side? Any thoughts around that?
Yeah, so I totally agree on the former. This is, a big part of the premise of Hdl21 is that exposing the kind of root level concepts, the sort of atomic things that these designers need. Like, we really need this sort of low level stuff exposed in a nice, approachable format. And so this is, PDK master, or at least what we saw of it the other day, is exactly the kind of library that I would recommend using this. Layout, I really only dip my toe into, mentioning. We have these various piles of layout software, and I think there are a number of different camps there. The one that I think was shown a few days ago is very much more in Layout 21's camp of being what I call programmed custom, where the designer is really dictating the ultimate content of the layout, as compared to something like the digital tools use, something like P&R, in which the designer is really dictating constraints to an intervening sort of layout solver. So there's many potential ways that can go, and I'm happy to chat about it.
More questions? Or comments?
I'm curious if you could daydream for a minute about how behavioral languages might fit alongside something like this. So let's say you have a Verilog A description of an op amp, and you've now constructed a schematic using this tool. How would you imagine sort of interchanging between those two representations and sending that off to a SPICE class simulator?
So the interchange between views is a thing that Virtuoso, so Cadence, does sort of natively. There's this configuration GUI. You can certainly imagine having such a first-class thing. Hdl21 does not. What it really has and allows you to sort of freely dictate the content of what these things are is it essentially has its internal notion of modules, and then it has essentially headers to external versions thereof, which are called external modules, which I don't have the best slide on, it seems. But they are, in fact, the same things that I'm showing defining in the PDK, which is essentially a Python native thing, or a sort of Hdl21 known thing that is, here are the ports, here are the parameters. It's going to be up to you to include it in some downstream external program or link it in by whatever way you see fit.